Hello, and welcome to what I now believe is the last part of lesson 8.7. This is hopefully going to clear up a few of the questions that some of you had on exponential growth and decay. I didn't realize that last worksheet I had kind of went into these types of problems, so I do apologize for that. Exponential growth, we kind of talked about it, I know, in one of the previous videos. It's still in the form of y equals a times b to the power of x. But the one thing you have to realize, and I think like I said, I mentioned this before, but the key thing with growth is that the b value has to be a number that is greater than 1. Okay? Whatever that number is that's greater than 1 is what we call the growth factor. Now, what this box here doesn't tell you is that sometimes you have to actually calculate that growth factor. So I kind of like to think of the b value, so I'm just going to write b down here, is really equal to 1 plus, and I'm going to put r, and the r here is really going to be the rate. Okay, so if you are told that a population is increasing by 2%, what we would do is we would take that 2% and we would rewrite that as 0.02. So I'm going to just say a 2% growth rate is going to be written as r equals 0.02. So if I wanted to calculate my b value, then I would really have 1 plus 0.02, which really gives me 1.02 when all is said and done. So my growth factor would be the 1.02 together. And again, if you notice, 1.02 is greater than 1, which tells me that I have something that's growing, or an exponential growth problem. Now the part A is going to be usually whatever your initial amount is. So if you're looking at an initial population, and let's say there's 1 million, okay, and you have a 2% growth rate, your initial amount for A is going to be the 1 million, and then the B would be that 1.02 for the growth rate, and then typically the X in this case would be like some amount of time that it's going to be growing over. So to look at an example on this, example 11 says, since 1995, the daily cost of patient care in community hospitals has increased about 4% each year. In 1995, such hospital costs were an average of $968 per day. So part A wants us to write an equation to model the cost of hospital care since 1995. So what we are going to do is, we know that this is an exponential growth. So I have my y equals a times b to the power of x. Okay, so I'm going to start out with my y equals. And in this case, remember, a is our initial amount or our starting amount. So I'm starting out with $968 because this problem is kind of based off from the year 1995. So in 1995, we know that the average cost was $968 per day. So that's 968. And then my b value is really going to be, because it's growing or increasing, it's really 1 plus my r value. Well, my r value is this 4%. So 4% as a decimal is really equal to 0.04. So I'm going to go 1 plus 0.04, and we're going to raise this to the power of x, or because it's talking about time, you could put t for time if you wanted. So if I go through and I simplify this, I get y equals 968 times 1.04 to the power of x. Now, just because we like to double check ourselves, okay, when I look at this, this 1.04 is a number that is greater than 1, which tells me that I have something that's growing or getting bigger. And if I come back up here into my problem, it tells me that the patient care in community hospitals has increased, which means it's also growing. So that's kind of like a good quick double check to do. So for part B then, it says use your equation to estimate the approximate cost per day in 2010. So I'm going to use that equation that I just came up with up above, that y equals 968 times 1.04, and I'm going to have to plug in some value for x. Well, and this is where things get a little tricky sometimes. So we want to know how much we're going to pay in the year 2010, but if you remember, we are basing our numbers off from the year of 1995. So 1995 is actually when our time is equal to 0. So 2010 then is going to be 15 years after 1995. So I am actually going to plug in a 15 for the x value. When I plug that value or this equation into my calculator, I can see that the cost in 2010 is going to go up to $1,743. And if we put the change in there, I got 3.2. So roughly $1,743 is what it's going to be per day in 2010 versus the $968 per day back in 1995. When you are dealing with exponential growth and exponential decay, a very kind of classic example that is used is what we call compound interest on different amounts of money that you put into a bank. So compound interest, when you hear this phrase, is when the bank will pay you money, okay, or interest on both the principal and the interest that you have already earned. Okay, so like if you have like a savings account, okay, and you put $100 in, then the next month you're going to get interest, okay? And then what they're going to do is when they go to pay you interest on that third month, they're going to pay you not just on what you put in the first month, but they're going to pay you on the interest that you earned in the second month and the initial amount that you had before. So that's a good thing, okay? And when we talk about an interest period, the interest period is going to be the length of time over which interest is calculated. Typically, the interest period is usually on a yearly basis. So we would say like a 1-year basis. Now where you have to watch this, okay, is if they say that they pay interest like quarterly, so quarterly, this would tell me that this is going to happen 4 times per 1 year, okay? Biannually, tells me that it's probably going to be paid out 2 times per year. So you have to keep that in mind, because when you go to plug in values for your x and you're told that you're going to be paid out quarterly over the course of 2 years, you're not going to want to put in 2 for 2 years. You're actually going to want to put in 8, because you have 4 times per year and it's over 2 years, so 4 times 2 is going to give you 8 years. So you just kind of have to be careful when you're trying to calculate these. So if we look at example 12, it says, suppose your parents deposited $1,500 into an account that pays 3.5% interest compounded annually when you were born. What is the balance in the account when you turn 18? So the first thing I notice right here is that we are doing this annually. That means that interest is only being paid 1 time per year. So again, I'm going to set this up as an exponential equation. So I have y equals a times b to the power of x. Okay, my initial amount is A, or in this case, your parents put in $1,500, which was pretty generous of them. Your B value, okay, is going to be 3.5%, but I'm going to make that 1 plus, because this is an amount that's going to be growing, 0.035. Don't forget to convert that percentage to a decimal. And then we're going to raise this to the power of x. So this is my standard equation. So I end up with y equals 1,500 times 1.035 raised to the power of x. So then it says, what is the balance in the account when you turn 18? Well, because I'm getting paid every year, that means my x value then is going to be replaced with the number 18. So I really have y equals 1,500 times 1.035 raised to the power of 18. So now if I type all this in, I get 2,786.23, or $2,786.23. So you have to think, if your money is just sitting there and you don't put any more money in there and you're not taking any money out at 3.5% interest, you're going to make an extra $1,286.23 just for having your money sit in that bank. Okay, so now that concludes our exponential growth. Exponential decay is actually very similar. Except our B value now, because we're decaying or we're decreasing our amount, that means it's going to become less. So our decay factor, or B value then, is actually going to become 1 minus your rate. Okay, and you should have a number that is less than 1. And we'll see how this works here in our last example. For our final example, it says, suppose the population of a certain endangered species has decreased, it should be 2.4% each year. Suppose there were 60 animals in the given area in 1999. Part A says to write an equation to model the number of animals in this species that remain alive in that area. So again, I'm going to refer back to the y equals a times b to the power of x. Okay, and if I rewrite this with what I know that my initial amount was 60 animals, so that's going to go in for my A. My B value is either going to be a 1 plus or a 1 minus. Well, because it tells me that I'm decreasing, that also tells me that I'm going to be subtracting or decreasing from 1. So my 2.4% has to be converted over into a decimal, or 0.024. And then we're going to raise that to the power of x. So if I simplify, I end up with y equals 60 times 976 raised to the power of x. So this is the function that I'm going to use to model this data. Part B says, use your equation to find the approximate number of animals remaining in 2005. So kind of like the example that we did with exponential growth, we are going to have to plug in the same value. And we started out, our year 0 was 1999. So when I go to plug in my value for x, we're going to have to find the difference between year 1999 and the year 2005. So I have y equals 60 times 0.976. 2005 minus 1999 is going to give me 6 years. When I go and I type this into my calculator, I get 51.86. So this tells me I'm going to have about 52 animals left. Or in 6 years, our population has decreased by about 8. Please let me know if you guys have any questions over exponential growth and decay. Thanks, and have a great day.